To start 1212, we're going to talk a bit about some things that we mentioned at the very beginning of 1211 as well. So remember, at near the very start of 1211, one thing we talked about was the difference in phases. So we have solids, we have liquids, and we have gases. So between these three phases in 1211, what we focused on was that solids were things, there's my thing, my marker. So remember that solids had fixed volumes and they had fixed shapes. So what that means, for example, is if you take something like a book. So I have a book on my desk. This book is a solid. I can't it's not going to change its shape if I try to put it into a new container. I can't put it in a glass and have it change shape for the most part. I mean, yes, my book is bendable compared to a table, but it isn't going to turn into a glass shape if I tried to put it in a cup. So that's what makes it a solid. On top of that, this book is going to stay about the same size unless I do something like I do a chemical change. Like if I burn it, then it's going to change. But as long as it stays a book, it's going to stay the same volume of book. Now, next coming up, we have liquids. These still have fixed volumes, but they don't have fixed shapes. So, non-fixed shapes. So what that means, for example, is if I have a glass here, and it's empty, and I was going to try to draw a gallon jug. Okay, I'm going to draw a pint carton, because cartons sound easier to draw. Okay, I was trying to draw a three-dimensional carton. Pretend this is a carton of milk or something. I'm bad at drawing this. This is my best shot. If I were to pour it into this cup, it's going to do something like this. Okay, it's going to flow like this. It might be a little bit up the sides or something. But it's not going to be carton-shaped anymore. So if you think of another shape, like the gallon jug I wanted to draw, if I pour it, it's not going to stay shaped like a gallon. It's going to change into the shape of whatever I poured into. If I pour it into a glass, it's going to pour like that. If I pour it into a bowl of cereal, it's going to spread out into the bowl. So it's going to change its shape, but it's still going to be the fixed volume. I'm not going to expect if I take a gallon of milk that's full, I'm not going to be able to pour it into 4 different containers that are a gallon each and have it fill them all up. That's not going to happen. It's going to stay at 1 gallon of liquid. Or going with the SI units we use, if I've got a 2-liter bottle of something like a soda or some tea or something, and I pour that out, I'm going to still have 2 liters, even if I separate it into different containers. It's not going to suddenly become 8 liters. Now with gases, that's not necessarily true. These don't have fixed volumes or shapes. So that means that with a gas, if I were able to take all the air out of the room I'm in right now, and thankfully I have air because it lets me breathe, but if I remove all of it and I put a tiny bit of air in here from outside, like I put a syringe worth, it's going to spread out to the whole room. The reverse is also true. If I try to put more air into this, let's say we took a tire or something, I put a little bit more air into it, it's going to spread out throughout that space. So my room isn't going to change in size in a significant way if I add more gas to it. But it will have more molecules in the room. So unlike a liquid or a solid, that gas is going to spread out and just take the shape of whatever container it's in. Now, if you remember the end of 1211, there are some things related to pressure. So some examples you might think of, like filling up a tire. The tire technically changes in size a little bit because the pressure difference means it pushes harder and it's going to end up expanding a little bit, but you can still get a lot more air in that tire than what was initially at just 1 atmosphere of pressure. You can put a lot more in there. So this was the 1211 part. Now in 1212, the part that we added was we were going to talk about the molar volume and density of these things. So we've already mentioned it somewhat. It's probably intuitive, but what's important is our solids and liquids are going to be more dense, whereas our gas is going to be less dense. So what we mean by this, if I take a set volume, what's going to turn out is there are going to be more molecules in my liquid or solid compared to my gas. And that means that my liquids and solids are going to be able to contain more molecules in that space. And that's what's going to, and because they've got more mass, they have more molecules, that's what's going to, and the more molecules having more mass is what makes it denser, because it's in the same area. And this is a very significant difference, that there are a lot more molecules in my liquids and solids compared to my gases in the same amount of space. Now, In most instances, my solid is going to be more dense. However, the textbook you're working with points out that this is not true in the case of water. Water is actually going to be more dense in your liquid form. That's why your ice cube is going to float, because it's less dense. That's not usual for most solids. Most solids are going to be more dense. But the difference between the liquids and solids is this itty-bitty, is a small gap. It's still different. Whereas between liquids and gases is this huge thing that won't even fit on the screen in comparison. So, on top of that, we sometimes use a term called molar volume. So what molar volume means, it's how much volume you need to have 1 mole of your material. So your gas is going to take, you have to take a lot more volume of gas because there are fewer molecules until you get up to a mole. So these gases are going to have larger molar volumes. And it's just another word we use for this term. Whereas comparatively, solids and liquids are going to have smaller molar volumes. Now these things are always comparative to each other. But yeah, so if we're comparing those, those are the two new features we talked some about here. And I realize my face blocked the word volume on larger molar volume, but I predict you know how to spell the word volume because it's right above there. Now, the other reason we worry about phases, and what we're mostly going to deal with phases in this chapter, is the idea of phase changes. So in a lot of cases, what we're dealing with is the fact that solids can go to liquids, can go to gases. Note that there are some cases, and we'll look at them, where solids can go directly to gases. That's an issue too. But let's say we've got a substance that at this particular pressure and temperature we're working at, it can do all three if we just change one of those variables. So let's say we take liquid water. We take water that's an ice cube, and it's at atmospheric pressure. That ice cube, if you put it in your hand, is going to melt. That turns it into liquid water. Then if I take that liquid water and I put it in a pot and I boil it, when it boils, that's it turning into a gas. So in both cases, the way I'm changing that is I'm heating it up. I'm adding heat, and that'll let me go from solid to liquid and liquid to gas. Now, if I were to remove heat, I could do the reverse. So if I cooled it down and remove some heat, I could go from gas to liquid. I could condense. So we can also go, so gas to liquid, we're gonna remove heat. Remove, that was badly spelled. So we remove some heat, and if we remove even more heat, we'll turn it into a solid. AKA, that's how we're gonna make our ice cube, and this little mark didn't need to be here. Now, that's one way to do these phase changes. That's not the only way we can do it, though. We can also do this by doing pressure changes. So, for example, let me make sure I've got the ones I wanted to do. Yeah, we could reduce the pressure. We could have our cup of water, and if we reduce the pressure, if we reduce enough, we could get it into the gas phase. So we could reduce our pressure here, and we could end up changing it from liquid to gas. We can also do the reverse. We could increase our pressure of our gas, and if we do it enough, we'll be able to get into a liquid. So for example here, this increase of pressures, another thing you might know about. So if you've ever seen propane that we sell in tanks, that looks like a flask. Pretend that's a propane tank. I can't draw a propane tank to save my life. Well, I probably could you'd get it. So propane is gas at standard pressure and room temperature. But when you put it in a cylinder, you add a bunch more, you put it into a tiny volume, which you remember from PV equals nRT. If I put a bunch of molecules in there, I'm going to end up increasing the pressure as long as the temperature remains constant. So we get the pressure high inside the cylinder. If we do that enough, we're going to get to turn it into a liquid. And then it's going to take up less space also. And that'll be good for traveling with it. So we can take a whole lot of these gas molecules and take it wherever we need. But then when I want to cook with it, when I release a little bit at a time, it's going to come to atmospheric pressure when it gets released from the tank. And now it's going to be a gas, which is what I want. I want the gas molecules in there. We'll also talk about this in a bit, but you're actually going to have both gas and liquid co-present there. You'll have a bunch of liquid, but there'll still be some gas molecules there as well. Depending on the pressure you pick, you'll end up having some that stay in that phase as well. So that's something you may know for, okay, that's how you can use a pressure to change a phase of something. And we can also do this for changing things into solids. Pressure matters there too. And in a number of videos, we will look at some graphs that help us predict, using pressure and temperature, what phase a substance would be in. And that's really nice for something maybe we don't know what it's going to be. It's some substance we haven't worked with before. We can look at something called a phase diagram, and we'll look at those in a little while. Well, a long while, towards the end of the chapter. So, the reason we're worried about this is this chapter's primarily focus is going to be on what's called intermolecular forces. We're going to talk about how that's related to this. So, intermolecular forces, I spell very slowly, are going to be the forces of attraction between molecules. So what's important about this is that previously in chemistry, we focused on forces that are inside a single molecule. Things like covalent bonds. That was when you had one molecule, like let's say a water molecule. A water molecule has two covalent bonds. And so those were intramolecular forces. And so what we're going to worry about in this chapter is now instead the intermolecular forces. How does the water molecule I just draw interact with other water molecules? Well, we know from earlier in the semester that this is going to have a partial negative charge around the oxygen and a partial positive charge towards the hydrogens. Well, that means it's got a negative and a positive side. And we know that that negatives and positives can attract to each other. So this is going to lead to them being able to interact with other water molecules. As you might imagine, the positive sides will get close to the negatives. The negative sides will get close to a positive. So in general, the reasons these attractive forces are going to exist, all the intermolecular forces are going to come from these, we're either going to have positive or negative ions, or one way we're going to have intermolecular forces. Another way is we're going to have permanent dipole moments. So if you don't remember the term dipole moment, the dipole moment in a molecule has to do with the idea that, in the case of a permanent one, that there's a difference in charge such that one part of the molecule is more negative and one part is more positive. Such in this water molecule, the oxygen side is going to be more negative and the hydrogen side is going to be more positive. And that's true all the time for this water molecule. And so these permanent dipole moments can interact either with each other, like one water molecule and another water molecule can interact, or it can interact with ions. So we'll talk about this in more detail, but remember when we dissolved things in water, like sodium chloride, we drew pictures of that sodium and the chlorine, and they were surrounded by water molecules. That interaction there is an intermolecular force. Now, the other case we're going to talk about is we're also going to talk about how temporary dipole moments. And so these are going to come from molecules that don't have a permanent dipole moment, or it also happens in that case, but we're going to talk about it especially with those, where something like, let's say, methane. Remember if we have CH4? I'm still not the greatest with this tablet. So if I have CH4, we talked about that was going to be a nonpolar molecule back in 1211. While it may not have a partial positive and partial negative in permanently, what will happen is this molecule has electrons, and those electrons are going to move around. And temporarily, one side will be more positive and one will be more negative. And that temporary difference, while it's not permanent, is enough that it can interact with other molecules around it. And we'll discuss that in much more detail in the next video. So these are the different ways that we can have intermolecular forces. Now these have some names. So we're going to talk about, so first our types, and then I'm going to do some detailed stuff with each of these. So this isn't your only, just to mention, this isn't the only time we're going to talk about it. So types of intermolecular forces. And I still have not figured out a better way to make that faster to write. So types of intermolecular forces. So we're going to talk about something called dispersion forces. These are also sometimes called London forces, so depending on the source you're working with. And so these are going to be the ones that come from those temporary polarity shifts. So these are related to temporary dipoles. Then we're going to talk about dipole forces. These are going to come from permanent dipoles. So these are molecules that are polar, that always have a positive and negative side, and those are able to interact, and that's going to cause dipole forces. We're then going to talk about hydrogen bonding. So hydrogen bonding is a specific type of dipole force that occurs when hydrogen is bonded to oxygen, when it's bonded to fluorine, and when it's bonded to nitrogen specifically. And it's going to be a very strong dipole-dipole force. And so because it's so much stronger than many other dipole-dipole interactions, we give it a special name and we're concerned about it because it is so much stronger. And then finally, we'll talk a little bit, we don't spend as much time on it in this section, but we do talk about it some. We'll talk about ion dipole forces, which means that we need to have at least one actually charged molecule. For example, when you have sodium plus in water. And so water's polar because of those OH bonds. They can interact with the Na+, and so we get an ion interacting with the dipole moments, or the dipole moments of these polar molecules. So these are the 4 types of intermolecular forces. Now, in our next video, we will go into some more details about how these intermolecular forces work.